So, remember, the first chapter was exciting as hell. Appreciate you keeping it down. We're going through it. It was all definitions. Chapter 2 is where we got into histograms and stem and leaf plots, and dot plots and all that. Remember those a little bit? We'll find it. So no formulas really yet. Chapter 3 is where we hit the end of chapter 2 is where we hit the I don't know why you write this down, but you can write this down if you wanted to. Remember that? First time we saw the summation symbol, we knew what it meant because we knew what its meaning is in English, so we can interpret what this formula means. You don't really have to write down the standard deviation formulas from back then because I'm not going to make you do it like I told you. Sigma squared equals sum of x minus mu squared over n, stuff like that. Let's see, now we got into z-scores. By now you should know this. You should just know it. Then we got then we have the opposite of the z-score. We have this guy. Those two kind of go together. And then, of course, we took a turn into probabilities for a little bit. So we can put down all the probability formulas. What does OR basically mean for probabilities? Add. I say basically because you might have to adjust it for anybody who's in both because you counted them twice. And remember, a lot of the kind of problems I give you, you actually shouldn't use the formulas because they make it harder. Probability is based on counting. So if you have the whole situation, you just got to count the answers. You don't have to use a formula. What's the given? What's on the bottom?
The opposite.
No?
B.
Yeah, B. Given B. So I know that something from B happened. So that's what's going to be in the well, it goes in the bottom probability. All the things that could have happened. This says given that B happened, so that's got to be what goes in the bottom. And if B happened, what's the only way that A also happened? It's got to be in A and B. Alright. You can have emotions about these if you want to. And then we got this guy, and basically means what? Or means add, and means no. This is where I was walking, getting slapped in the face. You guys remember that? Or the Challenger exploded because the O-rings, putting multiple locks on your door. So you'd hope to God it wasn't also add, because 1% chance for every lock. That means if you put more locks, if you add them, you're getting more and more chance for somebody to break into your door. That's breaks your house. It's no good. So it's got to be based on multiplication. But remember these kind of problems where like pick a card out of a deck of cards, but it depends on if it's with replacement or without replacement. Do you remember those? The second guy might change if I throw the first guy out. So it's the without replacement. Cool. That's basically all the probability stuff right there. I like it. And then, so we have a section. So we come back. Chapter 5 is where we start doing probability distributions. We have the XP of X stuff. We have there. And then we have the binomial probability. that look familiar? One person shaking their head, yes. Nobody's shaking their head, no, so I'm not, that might not mean it. And if I have an NPQ problem, the mean is NP, of course, and that sounds familiar because it's part of the check to see if it's normal. If the mean is big enough, and if the NQ is big enough, that means it's in the middle, it's got room to go up and come down. That's why that's the check. Standard deviation, remember what the standard deviation was for NP problem?
NPQ.
Square root of NPQ. Holy shit, are people saying something? So that's good stuff to have all together. I mean, this is all binomial stuff. This is all very obviously x, p of x stuff. Right? In your favor. If I give you x, p of x table, you should gravitate probably towards these. Like and then chapter 6 came along. And that's where we start doing, chapter 6 was continuous distributions. We had uniform distribution in there. Right? The only thing that I really ask about there is stuff you can't write down here. It's the height. Find the probabilities. You got to know how it works. Nothing I put down here. And then we get into chapter 7, the normal curve, and we start doing z-score stuff for real. Right? I think z-scores, we look it up in the chart to find the area. Do 1 minus if you have to, all that kind of stuff. And then we get to, so we can put this down here again if you want to, just to be repetitive. And then we get into this kind of stuff. What is this all about? What the hell is this? Yeah, that's the standard deviation for... Definitely not. It's still a population standard deviation, but it's a standard deviation for groups of size n. So this is the one that works for individuals. This is the one that works for groups of size n. I love playing freaking stairs. So this tells you how spread out individuals are from each other, from their own average. So if I took individual grade ages in here, standard deviation would tell me how spread out all those data points on average are from the middle. If I took groups of 5 people at a time, this would tell me, one of these would tell me how spread out the group of 5 is from their average. Let's see, blah, blah, blah. And then you can put this down if you really want to. It's the same formula, really, just with all the X bar stuff in it. Same exact formula, so. But you can write it multiple times if you want to. Let me see. Yep. And then we get into confidence interval stuff immediately after that. We have the 5 formulas from that. This is where we introduce the idea of t-score. And the 2 other formulas are for if I want to know how large of a sample I have to take to control my error. That's confidence interval stuff. And then, of course, we got into hypothesis tests. Everybody's here. So then you got Z star. This is the same old formula from before, so you can write it down again if you want to. Then you got Z star for percentages. And, the chapter 10 was an extra credit one. That's the one that's got 2 samples. So if you did that, you could put the formula down there if you want to, in case you give an extra credit one. And then we got into correlation and regression, for which there's no real formulas. You do it all in the calculator. And then we went back and did chi-square stuff. So I didn't use this little area here, so you can organize however you want to. Chi-square. That one. Cool. There's that other one we talked about, but again, I'm not going to put it down there. You know, wasn't part of the homework, so. Damn. That's quite a bit we did this semester. So anything else you think that I might have missed up there? I think I got everything. Okay. So now you can do whatever you like. We can talk about the practice final. We can talk about the quiz you just got back. Everybody has a practice final, right? The one that's not on the answer key I just ran out of room is number 11, so we're going to do that one together. So if you have the practice final, why don't you take a minute and try to do number 11, and then we'll do it together. And then I'll open it up to whatever you guys want to talk about.
I didn't mean to test or make that.
Oh.
Yeah.
Gabrielle.
Yeah.
By the way, everybody notice on the updated grade sheet summary, there's my office hours for next week. Next week is totally different. Monday's a holiday, so don't come here. No more normal classes after this week. Next week is all finals, so everybody's schedule is going to change. So this is my office hours for next week. Our test is on Wednesday, so it's not much time. That's good, actually. You don't want it to be the following Monday and you forget everything. What else is on there? I put on what you need to make on the final to pass, what you need to make on the final to get a B. I gave you a way to figure out if you want to get an A, just because I ran out of room. Cool. Okay. Oh, water. Anybody else not get their stuff back?
And then is class on Monday? Is class on Monday?
Monday's a holiday, and if it wasn't a holiday, it would be final exams.
Oh, so,
Yeah.
okay.
So today is the last day of normal class, right? Some of you guys are like, this is not a normal class.
So you know how we were able to put things in for the final? Like the test corrections? Is that today or can it be turned on Wednesday?
So the last test corrections are due the day of the final.
Okay.
Homework corrections are, of course, due the day of the final. Anything you haven't corrected. The quiz corrections are due the day of the final.
Okay.
Anything else you haven't corrected, you won't get as many points back, but if you get enough right, you'll get something back, right? So that all helps. The day of the final, I have the spreadsheet up here so you can make sure everything's right. If there's anything I've got in there wrong, I'm missing homework or something.
All the quizzes you can still turn in and correct?
Yeah, you can still
Okay.
do quiz 1 corrections.
But only the last test, right?
No, you can still do test 1
Oh,
corrections. Yeah,
okay.
it's just very late.
Okay.
So, you might not get any points back, but you won't get less than what you got. So,
Mhm.
and it's all review. The final's going to be cumulative, so it's all review.
Mhm.
And just make sure he was on the right track. It's very cool. This, for some reason, I always get people that mix these two up. I mean, this is what I actually saw. This is what I actually saw. What goes here?
Whole time.
Yeah. So I expect it to be 13% of the students to make an A, and I have 342 students. So 0.13 times 342, 44.46. So see how it repeats here? So how many F's would I expect then? 44.46, because it's still, I expect 13% to be F's.
And you want us to round, like, or you want us to put, like, the whole thing? Like,
Put the, yeah, you definitely want to put the decimal. And I'm going to show you, I'll show you how to do this in the calculator, in the lists. Remember list 1, list 2? So you don't have to put all the decimals down there. So how many B's? 20% of 34 point, so okay, I'm doing it in my head as I talk to you. 68.4, yeah. So again, it'd be for this one also, 68.4 is what I expect, because they're both 20%. And then how many C's do I expect?
116.28.
I like it. Go, Joe. Cool. Now you don't have to do this, but what should all these happen to be? 342. 342 because that's where they came from. They are groups out of this total group of students and how they are distributed amongst those grades. So they got to add up 342, or else there's some students who are like floating around. I don't know who those are. So let me just go ahead and show you this, because otherwise I'm going to go crazy with this. You can use your lists to do a lot of this work for you. This is just subtracting and squaring and stuff. So if you put in there 53, 63, so forth, and 44, 46. Just to show you, I don't think we've done this yet, but just to show you, I could put in here 0.13 times 342, and it'll do it for me, bam, right in there, right? And now L3, just to cut to the chase, let me see if you guys can handle this. I'm just going to make L3, I'm going to make it L1 minus L2 squared divided by L2. Let me stop there for a second. Where are the expected stuff? L2. So where there's an E, I'm going to replace it with L2. So L3 is going to be, when we go up to L3, L3 is going to be parenthesis L1 minus L2 squared. Now if I just do that, it'll give me this column here. So I could put it there. 72.932. Blah, 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 blah. And now if I do L4, if I make that L3 divided by L2, that's where the expected are. I'll get what we need to put there. So I got this is the important one. 1.6404, 42632, 1.86, blah, blah, 1.03, blah, blah, 2.01, blah, blah. The nice thing is you don't have to be as precise on the paper because you can actually have the entire thing in the calculator. Yeah?
Once again, how did you get L3? Is it L1 minus L2?
I just did this. So where are my O's at?
L1.
L1.
Oh,
So I did L1 minus, and my E's are in L2 squared. And the last one is going to be that divided by L2. So here I did L3 divided by L2. I like that. At this point, I'll take any reaction, but that was a good reaction. So now, how do I get, what do I need to do with all these? How do I calculate my chi-square?
The sum.
Yeah, just gotta sum these up. Now remember, to do it on the calculator real quick, I can quit out of this, go to list, list, math, sum, where was it? L4, I think, right? Whether there, yes. So you get 6.975. That's what it got. 6.975. That's my calculated chi-square. Now notice how I don't tell you an alpha, so what does that mean? You can't do it. Now, what's the most used alpha? 0.05. Yeah. Now, 0.05 is the most used alpha. So what's the critical score that leads to? So we already got this chart here. Little Dragon Balls and chi-square.
You said 0.05.
Yeah, it's the most used one. Alpha 0.05 is the most used. 95% confidence interval, most used confidence interval. So 0.05. And what's my degrees of freedom? Degrees of freedom. 4. Good. There's 5 categories. Minus 1 is 4, so I go to 0.05 and I stop at 4. 9.488. Did we make it far enough? No. We made it here. Which means what? We failed to show that these grades, if we did make it out there, it's so far away from 0 that would be evidence that these grades don't follow this pattern. Because they would be really different. We got them to be different, but did we get them to be different enough? No. So we failed to show that these grades don't match this pattern.
So you could just write their,
It looks like they do follow the pattern.
okay.
Yeah,
That's
you
fine
can just write
enough.
that. Yeah. It looks like they do follow the pattern. Officially, we would say, we didn't find enough evidence to say that they don't. But of course, English people have a problem with that. Double negative. As a test result, it's fine. Yes?
How did you get 0.05?
So again, I think in the book it actually says this in some homework. 0.05 is the most used one.
So you just use it.
If it doesn't say, you use 0.05. It's just the standard. If it's not 0.05, you have to say what it is, because then it's not the regular standard one. So if it doesn't say, you're like, oh, they went the regular standard one, the 0.05. Now on the test, I'm going to say it just in case, just so you don't get all freaked out. I'll tell you what alpha to use. So what if alpha would have been 0.10? Would this be different?
We still would have known.
Yeah, it still wouldn't be enough. It makes it easier to pass, but we only got 6 point whatever. You still would fail. It still would look like they do follow the pattern. Yes.
So alpha is a rejection zone, right?
Alpha is the area in the rejection zone. It's the probability. Huh?
If we don't make it, if we do make it in there, it's rejected. No.
Yeah, we can reject that they follow the pattern.
Okay.
Yeah. Well, we didn't make it in there, so we failed to reject that it follows the pattern. Yeah. Which, in plain everyday English, you could just say, it looks like they do follow the pattern. Couldn't say that they don't.
Can we maybe try another one of these, but like with a different
Sure.
answer?
Different twists. So what if I have, I don't know how to do this. There's really 2 main ways you see it. They either give it to you as percentages, the percentage for each category that you would expect, or they say it's uniformly distributed. You see what I'm saying? So if I said we expect a uniform distribution for whatever this is. observed expected. So we observe, let's say, so then we ask people how many, I don't know, it's not even kids or something. How many cars have you owned over your life or something? And we expect it, for some reason, we expect it to be uniformly distributed between 0 and 5. Now, how many cars have I killed? God, rode them until he died. So let's say that we talk to people and we get like 22 people said they've never had a car. That's neat. And then we get 48 say they've had one car. We get 46 say they had 2 cars. We get 58 say they have 3 cars. They've had 3 cars. 52 say they've had 4 cars. Where are we at, Jeff? Trying to make this come out decent. It doesn't matter, does it? Yeah, it does. 10, 94, 44, 226. Let's make this, what you got, Jeff? Just do it, we'll see what happens. Let's say this is 34.
Thank you.
So how many total people did I talk to? Don't look at me and say you don't know. You know how to figure out how many people I talked to. Yes. 260? 260. Now, if that's expected to be normally distributed, what does that mean? Yes, beautiful. I expect the 260 to be evenly distributed, so each category, but be careful, how many categories are there? There's actually 6. And that little 0 dude is evil. So each one of these gets 260 divided by 6. Do it again. 43.3 forever, right? Okay. So it'll be the same all the way down. The important thing to realize here is not the numbers, it's not anything. It's if I say we expect it to follow a uniform distribution, we expect the total number to be evenly distributed. Just like that, we did a die problem, right, where we rolled a die to see if it was weighted. We expect it to be uniformly distributed. That means all those should be the same. And they all have to add up to be 260, so they each should be 260 divided by 6 here. Cool. So now I can do, like we just did, I can do observed minus expected squared, and then observed minus expected squared divided by expected. Do it in the calculator if you want to. I'd say that's a good idea. Please notice I do not need to put 0, 1, 2, 3, 4, 5 in there. Right? Watch, right here you can put 260 divided by 6. Bam. Bam. Do it again, Joe. Bam. Yeah. But it would go too far. It would make the entire list. And it would make the whole thing bad. Does that, you understand? So if I do this equals, I don't know what to do with it. Right? If I did this equals 260 divided by 6. Yeah. Goes here. That's kind of ridiculous. I guess you can't do that. So too bad. I figured it would just make the whole thing that.
Yeah, I thought it did.
No. We go back. L3. So now I can make this observed minus expected squared. So this would be L1 minus L2 squared. Oops. Gotta go up here. So I'm here, observed minus expected squared. And then I can go L3 divided by L2. Bam. This one.
I need the sum of the
I'll show you. We're ready for it now, right?
Yeah.
Because I want, that last list is going to be this, and I need to get the sum of those to get my chi-squared. So again, if you go second quick, get the hell out of there. Go to second stat to get the list, because then I can do math on my lists. Math, I want to do sum, it's the fifth one. I want to sum up all four. I get 19.88.
Wait, I lost it.
Alright, here we go. Second stat. What you got?
Yeah, I got it. Step. Oh,
That's the chi-square for this. That's the calculated chi-square. So let me tell you this time, I want alpha to be 0.005. So what's the critical Java-Hutzel part? Oh shoot, I'm doing this on the back of my alpha equal to 0.05. Degrees of freedom here is
4.
no
5.
5.
Oh, 0. It's damn 0.
That damn 0. 0.0055 is 18.5. Oops, sorry.
No.
16.750. And we got to 19, so we're there. So again, what would a 0 chi-square mean? That would mean that the expected, the observed stuff
Does follow the pattern.
follows it exactly, right? So that would be chi-square equals 0. That means O minus E is 0 for everything. That means it's exactly following it. So the bigger chi-square is, the further away from following it exactly I am. So this is just the benchmark, because of the fact that this is a sample. There's got to be some far enough away. Just because we're different doesn't mean that that's evidence that everything is different in the whole population. There's some number I got to get past that's going to be like, holy shit, that is so different, the whole thing must be different. Again, that's the whole idea behind the Poisson test. Same thing. Did we make it far enough away?
Yeah.
Right? So we definitely made it way far enough away. It's further than this away from 0. So that's clear evidence that what? That's evidence that what? That in this case, the observed, do they follow the expected pattern?
Yes. No. No.
Just gonna crawl in. Alright, sorry. No! So again, hold on. That is really simple. I think you guys make 0 means they follow perfectly. In reality, it's always going to be some difference, right? There's always going to be some random wobbling. So this is the random wobbling accepted area. You're different, but you're not different enough. It's just random wobbling. This is like, holy shit, that's evidence that it's more than just random wobbling. That it's evidence that, holy shit, you got something different going on here. It's not following what we expected. So if it's something to do with cholesterol levels, it could be evidence that somebody's diet is better or worse, or the air or the water, or just magic. I don't know. Right? Yeah.
Because the last problem though, then what does the 0 mean from the last problem then that we just did?
Always the same thing. For goodness of fit, 0 would mean it follows it exactly.
Because
Go
when we
ahead.
weren't in the shaded area, it says that we were following the pattern.
Beautiful. I love it. Exactly. So this is evidence that you aren't following the pattern. That's
Okay.
right. So if you're here,
You are.
not enough evidence to say you're not following the pattern. So it looks like you are.
Okay. And then if you're in the area,
Here,
you're not.
holy shit, you're so far away from following it exactly that you're not following it at all.
Oh, okay.
Okay. Yes.
How did you get L2 with all the 43.3s?
Oh, 43.3 come from?
From dividing 260
Yeah.
by 6.
So I just went to,
Did you physically go in and put 43.3?
no, right here I put 260 divided by 6. Bang.
Oh, okay.
Yeah. So this is what actually is in there. I'm not rounding at all. So I'm not going to make any rounding errors. It's beautiful. Only math teacher would say it, but still, that's a thing of beauty. Rounding errors suck so bad. Rounding errors would make you, in a boat, take hours and hours to find the ship because you're off by 0.1 degree from your course. Over the course of several hours, that rounding error compounds. Oh shit, we're over here, we're supposed to be over there, we're all dead, it's bad. Right? It's not all die on a ship. That's Is that cool? I mean, so there's really only two ways we can give this to you. If I say it's uniformly distributed, you divide the total equally. If there's 7 categories, you divide by 7. They all get that. If I say 10% in this category, 20%, then you take those percentages of the total and you plop them in there, right? Okay. All right, so where do you want to go next? So that was a couple examples of chi-square stuff. So remember, I don't know if you guys, you only have to do up to 11.2, you don't have to do 11.6 for chapter 11.
Say that again?
You only have to do up to 11.2, you don't have to do 11.6.
Can that be, okay.
Yeah.
Is it 11.1 as well?
Yes. So you just have to do up to 11.2, not 11.6. So obviously, there's a few hypothesis tests. Hypothesis tests are a little long, I'm sure you might have noticed. So I can't put a ton of them on this. Like I said before, we're not going to have any more time than normal for the final. It's not going to be any longer. It used to be 3 hours. Can you imagine that? 3 hour stats test. Oh, yeah.
Is it 3 hours?
What's that?
Is it 3 hours?
All right. It's my fault for saying that. I'm sorry. It's 2 hours. It used to be 3. Forget I said that. It's 2 hours. Really? It's 5 minutes. Holy shit. I don't got 5 minutes in my day. What? Really? 5 minutes? Run? Let's see. Let's see what else is on here that might be weird. For some reason, like the problem, number 7. What phrase in there tells you the equation that you want to use? No. 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 How large a sample? Which means n. So then you go, oh, I want the equation that's solved for n because that would then tell me the answer. People make confidence intervals there and all that. I'm not asking for a confidence interval anyway. Right? If you've done it, I'm not talking to you directly because a lot of people do it. So that one is just an n equals problem. That's it.
What number?
7. Number 5. I used to be the second to the last data point in number 5. I used to live 1.5 miles away from. Anybody ever ate Bronx Pizza? I think they used to be better, to be honest. Bronx Pizza in Hillcrest. Anybody ever eat Bronx Pizza? All right, it used to be even better. Still tastes pretty good. So I used to think they must put crack in this thing. No, sorry, not the actual New York Bronx area pizza. I'm sorry. Yeah. I eat that with a fork. No. You fold it.
You do fold it.
Yeah. What?
Why would you fold pizza?
That's New York.
No, I do fold pizza.
Why?
Why would I?
Why?
Because it's almost like a stromboli then. Strombolis are awesome.
Oh, it's so true.
not pizza.
Yeah.
It's so true.
Huh?
Get that, not pizza.
No, because I want the option.
They've never had this cooked.
Anyway, all right. It's enough about the philosophy of folding pizza. What'd you talk about today in stats? We talked for like half an hour on folding pizza. So anyway, I do like to make a problem. Sometimes I've done a problem where I do Like it's not the football season right now, it's NBA season. So I would do something like number of points scored per game, number of points that the opponents score, and then the winning percentage. And then you can do a linear correlation to see which thing actually predicts the wins more often. Is it the offense or the defense? And for football, it was almost always defense, except a couple seasons ago, it was all of a sudden it was the offense that was a bigger predictor. But oh well, if you don't care about sports, I'll stop. But sometimes I also put census data down there. Like there's one problem with how the percentage of bachelor's degrees are higher versus the income level. You would expect those to be correlated, right? But I do, yeah. Anyway. So expect, you know that's going to be on it. And you're going to have to come up and show me your scatter plot and line of best fit, just like you had to do for that quiz. Let's see, number 4. Hopefully that looks familiar. What kind of problem is number 4? What kind of distribution is it? What kind of problem? Oh, I got to put this up. I know it's from May 2009, but I've just been too lazy to make an updated practice file.
Is that the N choose X?
Yes. What'd you say? It's a binomial. NPX. It's just staring you in the face. 9% believe that. Therefore, 91% don't believe that.
What
Right?
did you use on number 1? I thought, because I got so confused, I thought I used that formula on number 1.
Number 1 is a standard what kind of problem? Number 1, part 1. But what kind? There's a lot of probabilities. I mean, I tell you in the first part what kind of distribution it is. And number 1, part 1. It's normal. And I ask you to probably x greater than 200. So what are you going to do with 200? You're going to make it into a z-score so you can look it up on the z-score chart so you can get the answers, right? So you got to find that problem and do it. That's got to be the easy problem. Got to be. Find that problem, do it, right? Now, if it's not the easy problem, I'm worried about you. I'm already worried about several of you, but I'm even more worried. Now, what's different number 2? Why is number 2 a little bit different than number 1, even though it's going to be very similar? There's going to be one difference for the part 2 and number 1. This is part 2 and number 1. Huh?
You're gonna have to.
Part 2 and number 1.
It's, you're doing like a group instead of just a
Good. So what's going to have to change? Standard deviation is going to change. And then I do the exact same z-score formula, except I don't divide by 38.5. That's the old standard deviation. I divide by the one for groups of 32. Groups. Same thing for part B and number 2. Yeah. Okay. So look for that. You're going to see that 28% of people think that, blah, blah, blah. That's going to be the NPT problem. This one is, I give you a mean, I give you a standard deviation, I ask you a probability question. That's a z-score problem. Blah, blah, blah. On number 2, on part 2 of number 1, would I have to assume it's normal?
yes.
No. Yeah, because the sample size is big enough. I know it's normal enough. I don't have to assume anything. See, on number 1, part 1, I had to assume it's normal. Why? Because they didn't say it was. I have to assume it's normal to do that. Okay. Number 2 is your probability problem. 3 is, of course, this guy here, right? XP of X is given to you. Okay, so anything on there you want to focus on, or
You go.
which one? The quiz, sure, of course. You can ask questions of the quiz. I call it quiz 7, but it's actually quiz 6. But okay.
We're gonna get answer sheet for this, right?
Yes.
So for D, when I ask you if you could get credit rating, would you use the formula up top?
Yes. And why do you trust it? This is what everybody missed on part C. Why do you trust that line to make predictions on part D? Why do I trust it? because it doesn't look shady. I looked into its soul, and I could tell. Anyway, such a weird question. Think, why do I trust that line? Well, it's never done me wrong. Because the R value is close to 1. In fact, the R value is above the requirement for correlation, and beyond that, it's freaking 0.8 something or other, whatever you got. That was what I meant, part C. What does it tell us about the line of best fit? It tells us that we can trust it. And then what do I do immediately after that? I say use it. And you know you can trust it. Part D says use the line of best fit. Plug a 13. Everybody had 13, but there were 4 different versions with 4 different lines of best fit. So plug a 13 in, you should get somewhere around 73, 74. Yeah.
For the quiz, number 1, part C, it says the line of best fits with the data. Is that where we write like the sentence about why it fits? I didn't remember. I got it wrong.
Yeah, no, I spent the last minute talking about
Sorry about
that question exactly.
My
Yeah, Mr. Wall, I just want to tell you, I didn't listen to you at all. I want you to know. I love how honest you are. No, so if R is above the requirement, then there is correlation. The closer that is to 1 or -1, if it's negative correlation, the more and more I trust the line to make an accurate prediction. All right, so, yeah.
And for D, when you say use it,
Just plug a 13 in for X. Because what does X represent? The number of homeworks done. And I say 13 homework assignments, so okay, you're going to make X 13. And the output's going to be the current grade. Cool.
So when I don't know about mine, but when you circled my equation, I know you pointed because I got D wrong.
Oh yeah, well there you go.
But
I'm saying
did I
use
have-
that for part D.
Did I have the right?
Yeah. I didn't mark through it. I'm just saying this sucker, use it
Okay.
for part D. Yeah. And R equals 1 or R equals -1 means the points have to do what? They have to line up exactly on the line. That's what it means. That's perfect correlation. There's a homework question that says, if you have 2 data points where R is 1 or -1, does that mean it's perfectly correlated? No. And so many guys put 2 data points, and I'm like, all right, whatever, you got the idea. Any 2 points makes a line. It's when you have many, many points that make a line that's impressive. If you have 2 points making a line, it's like, good job. It's like me saying, watch me breathe. Watch, I can breathe. Hey, well, that's amazing. Watch me breathe on the water, you'd be like, holy shit. So 2 points making a line is like, well, that's what they do. That's what the freak 2 points do. Several points making a straight line perfect or really close to it, that's impressive. That means there's some pattern between the two, some relationship between the two, correlation. I can't breathe on the water, by the way. Don't see me near somewhere and push me in and go, come on, Mr. Bond. Come on. No, stop it. Please don't do it.
Number 6 is the hypothesis testing.
Yep.
Is that the only one on the practice test?
No. Number 9 and 10 are also hypothesis tests.
And you said there's 2 on the test, the actual final.
Well, I'd say at most 2. Because they're pretty long, so I can't put a ton of them on there.